So welcome to my talk, which is about multi-photon lithography and post-processes. As Margita said, I'm currently working in Vilnius University, which is in the capital of Lithuania, Vilnius. Vilnius University is one of the oldest university in the Baltics, and it's specifically I'm working in the Faculty of Physics at the Laser Research Center, where a lot of many laser technologies and laser companies that they are advancing, and they started from Lithuania, were born, and they are continuously blooming. Some words specifically for a Laser Research Center. It has different scientific interests and divisions. For example, advanced nonlinear optics, laser nanophotonics and 3D structuring, laser ultra-fast micromachining, ultra-fast spectroscopy, among others. But as you can imagine, I'm working in the laser nanophotonics and 3D nanostructuring division, specifically in multi-photon lithography, a 3D printing technique that has gained a lot of attention the last more than 2 to 3 decades. A lot of materials have been studied, a lot of fundamentals for MPL, and especially has been studied for different applications due to its capability and versatility to be applied, for example, in optics, life sciences, biomimetics, metamaterials, and metasurfaces. But why MPL? While there are so many different printing technologies, for example, like traditional photolithography, which relies on one photon absorption. Just a brief introduction, just a brief explanation. It starts with a liquid sample that is exposed under UV light, and through a mask it's becoming bulk, and we have the final structure after the development. However, this technique is limited to 2D or 3D. However, it has limited its liking high resolution, especially in the nanoscale, as you can see here, compared to results from multi-photon lithography. For this reason, multi-photon lithography has been the center of attention, and it's, as I mentioned, a laser direct writing technique capable of the fabrication of 3D structures in the micro and nanoscale. The fact that this technique is maskless is giving us the control of total control of geometry, which means we can print almost, maybe literally everything, even the last years, with high result features in the micro and nanoscale. And what is very interesting is that this can be applied with different materials and post-processes, as we'll analyze it. A brief introduction, how MPL is working is that a laser beam is tightly focused inside the photosensitive transparent photoresist, and by point scanning of the photoresist, we allow fabrication of a true 3D complex structure, which after the development is revealed. The mechanism that basically that usually MPL works is free radical polymerization, which requires the use of a photosensitive material mentioned as photoinitiator, apart from the monomers, in order to initiate the polymerization through the production of radicals, which is happening through by using multi-photon absorption process. However, as I said, MPL is established and has been studied a lot through these years. It is why I'm going through the fundamentals, is to show how important are the materials that they are used. For example, the standard materials that they have used, they have managed to advance MPL in the classic approaches to manipulate light. But in order to move forward and develop more intricate and alternative approaches to manipulate light, we need to go further, either in the new materials or studying the older ones in order to advance them. At the same time, post-processes also play a crucial role that we will discuss in this talk. And this, by altering the materials that we use in MPL or the processes, the pre and post processes, we can achieve maybe more extraordinary applications in life sciences and microscopy, in mid-IR technology, quantum, telecommunication, and even quantum, which is the hot topic of these years. So starting with the presentation, just a reminder that the most important parts of the MPL materials, it's the photoresist and the photoinitiators, and which both of them should hold the same properties, which is to be transparent in the wavelength that MPL is employed, to meet their absorption according to this relation here, to be regarding the PIs to be solvable in the monomers and materials that we are using, and of course to have high multi-photon absorption cross sections. Starting with materials, you may know that there is a variety of them, like organics, acrylates, hybrids, inorganics, and even functionalized. We will focus in this talk mainly on hybrids, as they have as they show interesting ways of functionalizing them. And regarding the PIs, you can see here a variety of them. Mainly, most of them are commercially available, and they are depending. Which one we are using is depending from their absorption and the wavelength, the wavelength that MPL is employed. So, starting with our first results from our latest publication from last year, it's about high and low fluorescent PIs for MPL. And why high and low fluorescent PIs? Why? Because it's one of the main properties of PIs, which can be an advantage or disadvantage, depending the application, is fluorescence. As you can see here, this is a standard material with a widely used photoinitiator called BIS or Michler-Stetton. These are structures fabricated with MPL, and you can see that depending on the excitation wavelength, they are always fluorescent, either lower or higher. For this reason, with our collaborator, Dr. Frederick Dumour, that he developed lab-made photoinitiators, some high fluorescent ones and low fluorescent ones. We study their properties in order also to understand what's happening when high or low fluorescence is taking place. Starting with the UVVs, with absorption spectra of the materials of the PIs, we can see here that for the high fluorescent ones, they exhibit a kind of similar behavior. If we are taking into account that the laser that we used for the characterization in MPL was 780 nanometer, they show a prominent absorption peak where 2-photon absorption will take place, while the low fluorescent ones, they show a bit more mixed results, absorption properties, which we'll discuss during the nonlinear optical properties that we found. So starting, the first thing we did was to develop a setup that we can somehow compact introduce the properties of these PIs. We started firstly by combining characterization techniques and, of course, the fabrication through APL. We started firstly with studying the PIs into the polymer, incorporated into the polymer, which was Z2080. And this was interesting because usually we don't study the PIs, the photoinitiators, inside the material due to the fear that we polymerize it before we characterize it. In this way, however, we used the polymerization in order to characterize them. So we used MPL as a tool for nonlinear optical characterization by developing a technique called, by using actually, a technique called 2-beam initiation threshold, which is using the laser beam that is split, as you can see here from the setup. The laser beam is split into 2 equal parts and controlled before being combined and directed into the MPL setup. Firstly, we determine the power of each beam, and by gradually increasing the power of each beam until we observe polymerization. And this is how we are taking its measurements, actually each spot from this graph. And in the end, we have this graph. And if once we fit it according to this equation, we can determine the number of photons that were used, the number n, in order to initiate polymerization. Here you can see the results from all the PIs. You can see that all of them, they have almost two number of photons, except the PIG, which has 1.5 photons excited in order to create radicals, which is of course not physically correct. We cannot have 1.5 photons. And what is happening here, what we assumed is that two processes are taking place, 1 photon and 2 photons. And this we assumed based on our the UVV's spectrum, because PIG showed an intense absorption peak at 300 nanometers, which is the second two number of photons absorbed, while there is also a smaller one at 500 number of photons. So we assume that there is a two process taking place at the same time. However, we also did it the standard way. We used the Z-scan technique to study the nonlinear optical characteristics of PIs in a solvent, and which is a standard tool used for NLO response of materials. And as you can see, we started with open aperture measurements in order to determine the 2-photon absorption cross-sections. And starting from the measurements, we can see here that we have a minimum transmission around the focal plane, while it's increasing, the transmission is increasing with the increasing of the intensity, which is this an indication and the proof that we have a typical RSA behavior of the PIs. At the same time, because we observed in the absorption spectrum that we have zero absorption at 780 nanometers, it means that we have a multi-photon absorption process taking place. Combining with the fact that the laser intensity, that the lowest excitation laser intensity was resulting in the appearance of NLO response, we can safely conclude that the NLO response that's taking place for the PIs is 2-photon absorption. What is interesting is here with the statistics, we can see that all the high fluorescent PIs, even the commercially available, they have lower cross sections than values of cross sections compared to the low fluorescent ones. And this was very interesting for later and for applications that they can be used. But moving forward, of course, we're speaking for high and low fluorescent PIs. We couldn't exclude the photoluminescent measurements, specifically from structures fabricated just simple cubes with MPL. And we can see here that the high fluorescent PIs, they have almost 2 orders, even 2 or 3 orders of magnitude higher PL signals compared to the ones that they are low fluorescent. And of course, we fabricated more intricate structures, specifically for the low fluorescent ones. We chose these structures. They are scaffolds that they are usually used for bio applications. And at the same time, we fabricated just some more bulky structures with a high fluorescent one. The one that exhibit higher fluorescence, to show that we can have also quite nice surface quality with these PIs. What is interesting actually is that we prove that by increasing, we can increase or decrease the fluorescence through altering the main components. So actually we can functionalize the material itself by changing its standard components. And at the same time, we observe that the fluorescence is not hindering the quality of the polymerization. However, as I said, PIs can be an advantage, but they can also be a disadvantage. They are photosensitive molecules. They're usually powders. They can maybe they're not dissolved in the material that we want to use. Maybe they show usually intrinsic coloration. They can be toxic for a lot of applications. So for this reason, we thought, what would happen if we didn't have PIs at all? And this is what we studied. We decided to study the standard material Z2080 without the addition of photoinitiator with 3 different wavelengths. So we started with the absorption spectrum, and we see with the standard wavelengths that we use later that we have a theoretical values of which multi-photon process is taking place. For when the material is excited with 570 nanometers is 2-photon absorption, with 780 nanometers is 3-photon absorption, and with 1335 nanometers is 4-photon absorption. As you can assume, we have for every wavelength, we will have different, as you see here in the design, different focal spot sizes during the fabrication. And this, however, was not a problem because we altered the parameters and we managed to fabricate, to have interesting results regarding the fabrication properties. Specifically for the green laser, we managed to have well-defined structures with a scanning speed actually as high as even more than the ones that they're used with for photosensitized materials. For the 780 nanometers excitation wavelength, we managed to have very decent high resolution for the process, which was about 250 nanometers. And finally, with the 1035 nanometers, which is a wavelength that lately is used for MPL, we saw that we can have very decent results in speed and in the intensity that was used for the fabrication. And of course, well-designed structures, fabricated structures. And still, fluorescence can be of interest. So we fabricated again simple structures of PI-free and PI photosensitized material. And we can see that independent of the excitation power of the measurements, PI-free material is almost 2 orders of magnitude. The signal of the PI-free material is 2 orders of magnitude lower than the photosensitized one. But one more step to understand them deeper would be, of course, to study the nonlinear optical properties of the PI-free material, which shows the 517 nanometers excitation for this case, and of course the Z-scan technique. And as you remember, this motif of the open aperture Z-scans shows that pure AZ, PI-free AZ exhibits 2-photon absorption process. Regarding the close aperture Z-scans, we confirm that it shows self-focusing behavior. So it's showing, the nonlinear refractive index, it's positive. And in total, the general conclusion from this could be that we can have nonlinear absorption and refraction of the PI-free material compared to the photosensitized ones because the volume fraction is dominant compared to a PI photosensitized material. Specifically here we can see the nonlinear optical characteristics. And what we saw from fabrication, now we saw it also from characterization aspect, is that we can have initiation of polymerization without the need of PI. But and due to the spectra also that we saw the absorption spectra, 517 nanometers was the most accurate for this purpose. However, we can go even a bit deeper in these measurements, and what we are observing through the years that we are characterizing Z2080 through simple linear techniques like absorption spectra is that we see always a spectral shift in emission and absorption when the PI is included in the material. And what is happening is that probably we have a donor-acceptor complex formation, which in order to be sure about it, we had to conduct NMR measurements in order to prove that indeed there is a chemical interaction taking place. And what we observed in the NMR measurements that there is a chemical shift of specific protons once the material is mixed with the PI or the PI is mixed with the material. And this is indicating a change in the electronic environment, which is consistent with the fact that there is a coordination of the photoinitiator's functional groups to zirconium centers. And indeed, actually, what we wanted to prove, and we prove it with NMR, is that the photoinitiator is chemically interacting with the matrix prior to the polymerization, which means that the raw material and the material with the PI are different, especially in chemical structure. And this was a very, I would say, deep insight that we had lately published. And this was by focus on materials. And what I wanted to say is that materials, by altering their standard components, which are the PIs, or by studying them with PIs or without, we can advance them, we can move forward, and we can better understand the process of MPL. However, it's not enough in order to functionalize the structures themselves. For this reason, the last a lot of years, post-processes are the tool towards functionalization of 3D nanostructures in order to apply MPL in a wide range of applications. And how this can be fulfilled, either by doping, which is one of the, it's a mix, it's a pre and post process for MPL, or by annealing, or by coating, specifically doping, for example, of phosphors in order to achieve electroluminescence, depending what are the phosphors, or by doping with quantum dots. This has been used a lot, and again, it's a very interesting part of MPL, doping of with quantum dots of the materials, as they can show a lot of different interesting properties for applications in nanophotonics, in sensing, or anywhere else. Of course, annealing is a process when the structure is undergoing intense heating to extreme temperatures, and this results in the transformation of the material to totally inorganic structures, while at the same time decreasing its overall size down to 50%, which can give us high resolution and, of course, for example, high refractive index depending on the material, and durability. And finally, I think coatings is the older post-process technique that is MPL is used for. MPL structures are undergoing. For example, it has been used for coating, for magnetic coatings, and for optical coatings like under-reflection coatings or high transparency. So I will start with the post-process of coating, which is the oldest, and it's a project of ours between Fourth and LRC is running the last 3-4 years, trying to understand what's happening. So what we wanted to see is what is happening if we move a material, specifically aluminum zinc oxide, that is used usually in 2 dimensions in a 3D environment. And we chose this combination because we wanted to have tunable properties in the telecom band, which is of high interest the last years. So what we did was to fabricate photonic crystals with multi-photon lithography and coat them with aluminum zinc oxide using pulse laser deposition in order to see their steady state and dynamic properties. We started with the development and the characterization of azo-thin films as preliminary results. We've, of course, then fabricated 3D photonic crystals through MPL and characterized them. And finally, we developed a hybrid 3D photonic crystal coated with azo and characterized its properties. But someone would say, why azo? Because azo the last years is of high interest due to its ENZ behavior, and specifically, it has shown it possesses metallic properties in the near IR regime, and making it suitable. It possesses also a Drude-like response, making it suitable for ENZ behavior, especially if we tune the carrier concentration. And by carrier concentration, I mean the amount of aluminum inside into the aluminum zinc oxide. Also, its ENZ regime has found to be 1,550 nanometers, which is the telecom band that we are interested in. It's highly transparent in the near IR, it's conductive, and the most important for us also is that it has been already studied with a variety of substrates, but always in 2D or stacks. And that's why we chose to go 3D and see what is happening and take advantage of the properties that MPL can give us. So instead of, we used a wood pile-like geometry, which is a kind of benchmark for developing photonic crystals with MPL. And we wanted to have something that is sure in our hands in order to continue, as this geometry has shown tunability, optical control and manipulation in any wavelength, especially in the telecom wavelength that we're interested in. It has shown nonlinearity, which would be interesting for applications such as optical switching in nanophotonics. And of course, although it's not straightforward, it is possible to be developed only with MPL. So starting with the results, firstly, we developed 3 different thicknesses, 3 different films of different thicknesses in order to investigate which one is more interesting for us. And we saw that in the transmission spectrum, all of them, they show the same behavior with being highly transparent and visible and near IR. However, in around 1,200 nanometers, we see that there is a decrease in the transmission, and this is due to the decrease of the permittivity of the change of the permittivity to negative values, which represents a metallic behavior and, of course, low transmission values. However, in this gray area is where the ENZ behavior of azo is found, according to previous works. Of course, because we're speaking for crystalline materials, we conducted X-ray diffraction measurements, and we saw that we have the hexagonal Wurtzite crystal structure of zinc oxide, as we expected, with the c-axis to be perpendicular to the substrate surface, meaning that we have the polycrystallinity that we want for the films in order to be highly transmissive, as we saw it. The valley probably is representing the amorphous aluminum. And finally, we also conducted atomic force microscopy to be sure what's the quality of the coating. And as you can see, the thinner one, the 150 nanometers, shows minimum to no grain formation, which means that the higher coatings, they were aggregates forming on the surface. And for this reason, we chose for the next of our experiments to use only the lower thickness azo coating. Later, we fabricated the 3D photonic crystals, VMPL. Here is the unit cell of wood pile geometry and all the dimensions. And we decided to fabricate 3 different photonic crystals, and by different I mean different in layer periodicities, which would give us a would give us different photonic band gaps. So we chose 1.2, 1.3, and 1.4 micrometers in layer periodicity. We had successful results. We had very good resolution down to 270 nanometers. And what was interesting for us, as 3D photonic crystals, although their geometry can be achieved, but to really have photonic band gaps is not so straightforward. From this this optical microscope image, we saw this yellow vivid color it means that the incident light of the microscope is reflected by the structure. So probably we have a photonic band gap, and we are not speaking only for a bulky cube. And indeed, from the FTIR measurements, we see that all our photonic crystals, they show a band gap, 3 different actually band gaps in the area that we're expecting according to previous publications and some simulations we have conducted. Before we move to the coated ones, this is what we wanted to have. We wanted to have a blue. The blue represents the polymerized line, so the simple line of the photonic crystal, while the gray is the coating of azo on the crystal. We wanted to have this kind of uniformity and smoothness. As you can see here from the magnified image of the photonic crystal, indeed we have this. We didn't make the structure bulky. And here are the results for all the 3 different in layer periodicities. We have, of course, an increase in resolution due to the coating, which is around 150 nanometers, but we didn't make the structures bulky, which was our biggest fear, I would say. Before we move to the optical characterization, we also conducted these measurements to be sure that we have aluminum, zinc, and oxide on top of the material, not other materials on top of the structure, not other materials that can be attributed then to the deposition technique. And here are FTIR results. Of course, again, we were very happy with the optical microscope image that we have a blue color, which means that probably there is a change in the band gap. And as we can see from the FTIRs, there is. What was very interesting for us was that we had a shift in the band gap to lower wavelengths for all the structures. So we didn't have mixed motifs. We had the same pattern taking place for every photonic crystal with the same coating. The most interesting for us was the one with 1.2 micrometers in layer periodicity, as it showed the photonic band gap closer to the ENZ regime of aluminum zinc oxide. However, all these measurements were steady state optical properties of azo-coated photonic crystals. But what would happen in a dynamic property? Because photonic crystals have shown dynamic properties and azo too. And this is a project that Professor Mikas Bengris in Vilnius University in the Laser Center is going through. He has developed a very complicated pump probe setup, and here are just some first results of these very small structures characterized through transient absorption. We see here an example of a transient absorption measurements of of the film of azo and the coated structure. And the interesting part is actually that we see a spectrally pronounced ultra-fast pump probe response, but only if we have the combination of azo with ready photonic crystal, which means that the coexistence of the photonic resonances of the crystals with the optically active azo is necessary in order to obtain such modulation. This is a very interesting project, and we are trying to understand now why and how this is happening. But moving forward, as I said, I will speak for coatings. Another project that now is taking place, it's almost done. It's the use of coatings in order to achieve high transparent micro-optics through anti-reflection coating. So what we did, we started with the fabrication of different same micro-optics with three different levels, 1, 2, and 3. And we coated them with using atomic layer deposition technique with coating of aluminum oxide and titanium dioxide. And we managed to have coated micro-optics with anti-reflection coating. And here are some first measurements of showing good quality optical transparency depending of how many levels we have. Moving forward, as I mentioned, there are I will discuss for 3 different post processes. We discuss for coatings, and the last 2 ones can be also combined. And this is actually what is the main activities of the lab the last years, especially when we are speaking for dopants like phosphorus, that they are combined with annealing due to in order to achieve the properties that we want. And this has been discussed in depth in our latest review from last year, where we discuss actually how this can advance materials engineering and NMPL for different applications and other different 3D printing techniques. However, a starting point was of this topic, of this post-process, was to combine AZ with doped with ytterbium, rare earth ion ytterbium, and it was very good for us, very important to be sure that the doping is not affecting the standard fabrication parameters of the material. However, we have not studied it yet in depth. I will study it in my MSCA postdoctoral fellowship named Assign, which I will try to advance the materials engineering in order to fabricate structures for the generation of shaped single and multispectral emission in the nanoscale. So this was the end of my talk. And as I said, it's very important for MPL to study the materials that we have already used all these years, understand them better, and then try to functionalize them either by altering the standard components or by post-processes like doping, coatings, and annealing. So these are the people that I would like to acknowledge. Most of them, they have acted as mentors to me. And of course, I would like to thank you for your attention.